Alright, hello. So if you're watching this, it is because you have to spend some time at home, either you're sick or you've gone away, and you're using this to just kind of catch up on what you have missed. So basically what we're going to be doing is that we're just going to go over topics that were covered in class. So this is still kind of going over how it would have occurred in class. We're using the exact same notes, exact same technology as we would have there. So this unit is our first one. It is entitled Thermochemistry. So we are going to be looking at what that entails, and of course everything that goes along with it. So let's look at the introduction. Now, of course, thermochemistry is just a study of the relationship between chemical reactions and energy changes. So that's going to be a recurring thing, is that this entire unit we're going to be looking at energy changes throughout. So this is going to be crucial for life. Not only we're going to look at photosynthesis, we're going to look at fuels and batteries and everything like that. So one of the first things that we're just going to look at is that how stored energy in chemical bonds, where they come from, and we're going to make the connection how they originate from the sun. Now, we're going to focus on fossil fuels or hydrocarbons because they are a major source of chemical potential energy, and we use them to this date to fuel our vehicles, to heat our homes, and making of a lot of different things as well. So it's very important. So as we know, fossil fuels originated from deposits of dead plants and animals that passed away millions of years ago. So we're going to focus on the plants though, because plants captured the energy of the sun during photosynthesis. Now, of course, animals ate the plants, which stored it as chemical potential energy in the body as carbohydrates, fats, proteins before dying. Now, of course, if you took any bio courses, you know that whenever you start either a food web or a food chain, you generally start with the sun, and then the sun going towards some sort of plant, and then something eating that, and then continuing on. So the sun is kind of important. Now, once these plants and animals died, time, temperature, and pressure converted these dead plants and animals with the stored chemical potential energy into the hydrocarbons we know as fossil fuels. So this is kind of a roundabout way, but the connection we're making is that the energy stored within chemical bonds of all the fossil fuels originally came from the sun. Now, this is one connection that when you sit down to write your diploma at the end of the year, this is a very common connection that they like to ask in your first few questions, like where did that energy come from? And it's going to be the sun. Now, we are going to be talking about energy, so there's two different fundamental types of energy. We have our kinetic energy, that is the energy of motion, or of moving particles, or the energy of, the motion of the particles. And potential energy is the energy that is stored in our chemical bonds. And thermodynamics, of course, is the study of the movement of heat energy between a system and surroundings. Now, we're going to make this connection really quick first, but our system is always going to be a chemical reaction. For chemistry in our surroundings, this is the one that's going to undergo a temperature change. So later in the unit, when we start getting more into this, this will make a little more sense. But when we talk about our system and our surroundings, we're looking at what chemical reaction is occurring and how is it affecting the surroundings. Now, when we refer to system and surroundings, or the types of chemical systems that we can have, there are three main ones that you learned before. So open system, closed system, and isolated. So open means that both energy and matter are able to enter and leave. Closed, only energy can enter or leave. And isolated, neither matter nor energy can enter or leave. Now, also because we are going to be dealing with energy transfer, we do need to be familiar with the first and second laws of thermodynamics. So the first law of thermodynamics states that the total energy of the universe is constant. So this means that energy cannot be created nor destroyed, so it needs to be transferred from one form to another. So the total energy of any system is conserved. Now, the second law of thermodynamics as well, this is the technical term for it. In the absence of energy input, a system becomes more disordered. What we are going to refer to this sentence is right here, and that is heat will always transfer from hot objects to cold. until an equilibrium is reached, which means until they reach the same temperature. So let's look at kinetic energy and temperature change. So we're going to be introducing our first equation right here as well. Now in Chem 30, you will need to memorize all your equations. There is no formula sheet. All right. So this is going to be one of the ones that we need to remember. So we refer to thermal energy as the total kinetic energy of all the particles in a system, whereas the temperature is just the average kinetic energy of the particles of a substance. So basically, a thermometer just averages or finds the speed of the particles that are there. So the kinetic energy changes when molecules either speed up or slow down. Therefore, the faster particles move, the higher the temperature. In heat, when we refer to heat, we're talking about the transfer of thermal energy. Right? And thermal energy, definition right up here. So heat energy transfer will be related to temperature change. That is going to be true all the time. And remember, only the surroundings will change temperature due to energy gains by the losses, or by energy gains or losses in the system. And remember, systems is our chemical reaction. So only the surroundings will undergo a temperature change. So that means our surroundings are going to get hotter or colder based on what our reaction is doing. Now, as you can see right here, our formula Q is equal to mc delta T. We do need to break down what these letters mean and, of course, how to solve for them. So our first one we're going to talk about is C, specific heat capacity. Now, these values, or as we see right here, there are going to be a bunch of different ones found right here. So if you look right down here at the note, this is value for specific substances are found on page 3 of our data booklet. So your data booklet, you should have something like this, and page 3 is right here. So we have a bunch of different specific heat capacities for common items. Now, in questions and stuff like this, if it just says air, polystyrene cup, copper, aluminum, iron, tin, or water, it's assumed that you're going to find the specific heat capacities here. If it's something different, hopefully the question will give you the specific heat capacity if you're supposed to use it. So, now also you'll notice that the units here are in joules per grams degrees Celsius. However, we can use any of these units. So joules per gram degree Celsius, joules per milliliter degree Celsius, kilojoules per kilogram degree Celsius, and kilojoules per liter degree Celsius. Now, as for the ones with volume, the reason for that, the density of water, so 1 gram is equal to 1 milliliter, and 1 liter is equal to, or sorry, I'll try to keep the mass first just so not confuse ourselves, and 1 kilogram, I don't know why that turned that color, 1 kilogram is equal to 1 liter. So that's why when we see right here, joules per gram and joules per milliliter match up, is because 1 gram of water is equal to 1 milliliter, and same thing, we get our kilograms and liters match up as well. So I'm just going to show you on how these units are equivalent using dimensional analysis. So if you remember from Chem 20, dimensional analysis is changing the units for something so they turn into different units. Now we're going to start with a hypothetical specific heat capacity is at 1 joule per gram degree Celsius. Now we're going to convert this into, so it matches this, kilojoules per kilogram degree Celsius. All right, so we're going to convert one to the other. Now, if you remember, when we are doing our conversion factors, the unit that we want to cancel out needs to go on the bottom, and the unit that we want to come out at the end is on top. So we want to convert our joules into kilojoules, so that means our kilojoule unit needs to go on top, and our joule unit needs to go on the bottom. Now, what we do for our numbers, we know that in 1 kilojoule, there's going to be 1,000 joules, because remember, kilo just means 1,000. So when we multiply these together, the unit for joules is going to cancel out, and we're left with kilojoules. Now, I also want to convert my grams, so I'm going to do that in my next conversion factor. Or in this case right here, I want kilograms in my denominator, and I want to cancel out grams, so I have to put grams up on top. Now, same thing, we have 1,000 grams in every 1 kilogram. This way, our grams cancel out, but also we're going to notice our units of 1,000 cancel out, and we're left with 1 kilojoule per kilogram degrees Celsius. So the unit that we have in front here, this 1 doesn't change. So that's why we can use all of our units in our data booklet right here, all these units are interchangeable. So what that means, for example, water has a specific heat capacity of 4.19 joules per grams degree Celsius. This means that it takes 4.19 joules of heat energy to raise the temperature of 1 gram of water by 1 degree Celsius. And then, of course, as we're going through, if you want to flick over to that data booklet, find out the specific heat capacity for copper. The specific heat capacity of copper is 0.385 joules. Oh, that's an ugly looking J. Let me erase that. Go back. Joules per gram degree Celsius. Now, let's get into calculations. So for energy calculations, this is just to determine how much heat energy is transferred between system and surroundings. So there's a few things we need to know. First, we need to know the mass of the substance undergoing a temperature change. We also need to know what is the temperature change. And of course, we also need to know the identity or the type of substance so we can get its heat capacity. So let's look at our equation. So we have Q is equal to mc delta T. Q is going to be the heat energy in joules or kilojoules. Mass is going to be in grams, kilograms, milliliters, or liters. Temperature change is going to be in degrees Celsius, and we always take the final minus the initial. And C, specific heat capacity, we have our units here that was listed on the page. So what it says right here, pay attention to the units for Q, M, and C. They must match in order for the equation to work, which we will get into. Now, also a special note right here, if the temperature change is negative, the temperatures decrease, so a negative value will make Q negative, indicating that heat left the system. All right. Therefore, the Q tells you how much heat was exchanged between the system and the surroundings. So we're going to pay more attention to this later when we get into calorimetry, but just for right now, we'll kind of bring this up as we go. All right. So find the heat required to change 2.50 grams of water from 10 degrees Celsius to 25 degrees Celsius. So we know heat required, so solving for Q is equal to, we don't know. Now, what we have right here, we got 2.50 grams of water. So mass of H2O, you don't need to write the subscripts there, I just like to do it so I know what I'm dealing with, is 2.50 grams. Specific heat capacity, also make sure it's H2O, we're going to have 4.19. Now, because we have a mass of water in grams, when I look at the values for C, I want to make sure that the units match up. So therefore, I need to use this value. Because where we have our mass in grams, I need to use a C value that has grams in it. So that means it's joules per gram degree Celsius. So I write joules per gram degree Celsius, and delta T is equal to TF minus TI, and that is equal, well, it's from 10 to 27, so we got 27.0 degrees Celsius minus 10.0 degrees Celsius, and we're left with 17.0 degrees Celsius. Cool. So these are all of our givens. Now for solving, we write our equation. Q is equal to mc delta T. Now we put in our values. So M, 2.50 grams. C, 4.19 joules per gram degrees Celsius. And delta T, 17.0 degrees Celsius. Now the reason we need to pay attention to our units, because look at dimensional analysis, we can tell that the units of grams cancel out. The units of degrees Celsius cancel out, and we are left with units in joules. So that means our answer, Q, is going to equal 178 joules worth of energy. Now, for our next one, this is when it's really going to be prevalent on why we need to pay attention to our units. So, let's look at example 2. We have a 250 milliliter glass of water at 20.3 degrees Celsius is placed in a fridge for 25 minutes. If the water lost 2.320 kilojoules of energy, what was the change in temperature? So, we got Q. Hold on. We got Q is equal to 2.320 kilojoules. M is equal to 250 milliliters. C is equal to, I'm going to get to that one now in a second. So delta T is equal to, it says here, the glass of water. Oh, delta T is equal to, we don't know. So C, we know it's water. So we're going to write 4.19. Now, look at the units of energy and water. We have kilojoules and milliliters. So when we scroll up to the top, here we'll notice, try to get a C value that has both kilojoules and milliliters in it, and you won't find it. Because when we have milliliters, our energy needs to be in joules. When we have kilojoules, our volume needs to be in liters. So that means we need to convert one of them so that the units for C will match. Now, at this point, you can convert whatever you want. I always like converting milliliters into liters because we just divide by 1,000, and that's, for the most part, with chemistry, we should be used to converting milliliters to liters due to our concentration stuff. So this is just 0.250 liters. Now we can have our C value. Let's put that in. It should be in kilojoules per liter degree Celsius. And now kilojoules, liters, they match. So you go Q is equal to MC delta T. Now, if you want to just pause this video and write it out, you can see if you get the same answer, but I'm still going to go through everything. So we need to rearrange for delta T is equal to Q over MC. Delta T is equal to 2.320 kilojoules over 0.250 liters and 4.19 kilojoules per liter degree Celsius, and we are left with delta T is equal to 2.21 degrees Celsius. Now, where this one's just asking for the change in temperature, we know that it's changing 2.210, but it's also placed in a fridge. So we know that if we wanted to figure out the final temperature, we can inherently just subtract 2.21 from our 20.3 and get the answer. Now, another way that we can do it is that if you scroll back up to the note right here, it says that if heat leaves, it should be recorded as a negative. And we know that if something is going to be replaced in a fridge, well, this energy value technically should be listed as a negative, and delta T is negative, knowing that the change in temperature is going to decrease because we placed it in a fridge. Now, for this particular point in time, like I said, it was kind of mentioned here, but it's not that important because we can intuitively know that 2.21 should be a decrease because it was placed in a fridge. When we get to something called calorimetry, it's going to make a huge difference, but there's a different equation for that as well, where we're really going to pay attention to energy lost or gained. So right now, not that important, but just have it in the back of your mind. And our last thing we're just going to look at is, this is an old diploma question, so you should definitely want to pause the video and try this one. So I'm just going to circle the answer and give a little explanation right here in about 3 seconds. All right, so pause it and try to figure this one out on your own. All right, so for this right here, hopefully you got the answer is A. The reason for this saying, which one will undergo the smaller temperature change? So when you look at specific heat capacities for aluminum and tin, I believe, when we go back, data booklet, tin, specific heat capacity 0.227, aluminum 0.897. So what that means is that it takes more energy for aluminum to raise its, like 1 gram of aluminum 1 degree Celsius. So when we look at each one's tested, they have the exact same mass and they're transferring the exact same amount of energy. So if it takes more energy to raise 1 gram of aluminum 1 degree Celsius, obviously it's going to have the lower temperature because of the larger specific heat capacity. And the one with the lower specific heat capacity is going to have the higher temperature because it takes less energy to raise its temperature. All right, so that is it for our lesson 1. Now, inside, after this, you should have a workbook as well that goes along with these here, and it should be correspondent as well with section 1, just changes in energy. So you definitely want to go ahead and complete this as well. So on Google Classroom, you should see the answer keys and blank copies of both the notes and the answer key for that in the workbook. So please do that, and yeah, just give it a try, and if you have any questions, make sure to contact me so we can figure stuff out. So hopefully this is helpful, and I'll see you guys maybe for the next the next lesson on energy and enthalpy.